questions over any of the assignments so far? Well, today's lesson is actually probably going to be pretty short. It's probably not going to take the entire time. Because what we're going to be talking about is kind of still with complex numbers and plotting them in these points. Now, we can plot a complex number of a plus bi in the complex plane. And the reason we call this the complex plane is it's broken into two main parts. We have the real part and the imaginary part. So our x-axis is going to be considered the real plane, and the y-axis is going to be considered the imaginary plane. So whatever the a value is, our real part is where we're going to go on the real axis, either positive or negative. And the bi, the b value, is where we're going in the imaginary plane, either up or down. So the point 3 plus I, we would go over 3 and up 1 to I. Or negative 2 minus I. Negative 2 in the real, negative 1 in the imaginary. And we can plot these here. Now we can also find the absolute value of a complex number. And the absolute value of a complex number is just the square root of the real part, or the real number, plus the square of the number in front of I, or our b value. And we get this here. Whenever the complex number a plus bi is a real number, that is, b is 0, then it's really just saying the absolute value of a. So we're going to plot and find the absolute value of this number here. So if we plotted this point, negative 2 plus 5i, well, the a value is negative 2. The b value is 5. So we would go negative 2 on the x, and we have 5 on the y, which this point here, negative 2, 5, would be our complex number. So we use the real and then imaginary. Questions on this here? Now, if we want to take the absolute value of this complex number, we're taking the square root of the a term, so negative 2 squared, plus b squared, which is b 5 squared. Now, at this point here, if we wanted to type this onto a calculator, we could, and it would give us the answer. Or we can do this by hand. Negative 2 squared is 4. 5 squared is 25. So the absolute value of this complex number is going to be the square root of 29. 29 doesn't reduce, so we just have the square root of 29. Questions on this here? Questions on anything we've done so far? Yeah, that's it. Yeah, there's really not. So we'll do one more of these. Plot and find the absolute value. Well, might as well go on and find the absolute value. Absolute value of 3 minus 4i, which is going to be the square root of 3 squared plus negative 4 squared. Well, 3 squared is 9. Negative 4 squared is 16. Which gives us 5. Kind of makes sense. Now, if we graph this, so we would go over 3 and down 4. Now, the absolute value does make sense because really we're just finding the distance from 0. And we're told that the side lengths are 3 and 4, so the hypotenuse is 5. That's also where we got the square root of 29 on the last problem. It's just the distance from 0. or the length of that vector. But that's it. Well, if I ask you just to find this here, find 1 plus 3i plus 2 plus I, if we wanted to just find that, well, we would add them together, and we would get what? 3 plus 4i. And that'd be the answer. Now, this is going to be, and that's all I'm going to ask, especially on the homework, when it just has to add in the complex plane, just go on and add them. Now, what it's actually getting at is a little bit more than what we've done, because we didn't cover vectors. Really what we can do is adding vectors, and I'll show you, is we would plot them in the complex plane. So 1 plus 3i. So 3i would be here. 2 plus I would be this here. So we'd have these 2 points. Now, what I'm going to do next is a little bit, not so much cheating, but is cheating, because I have technology. So we have these 2 vectors, essentially, going from the point, from the origin to our point. And when we add 2 vectors together, we put head to tail. So I can move the vector and add it to it. And where the starting point to where we're going, different color, ends up being our new one. And is that the point we got? Yeah. And that's how you can add vectors together. You're just putting head to tail. Or if you wanted to subtract vectors, you put tail to, or put head to head and go in the opposite direction. So there's different ways we can do this, and we ended up missing out on this. And if you go into a lot of engineering, they'll pull vectors back up. They'll go back through it. There's not a ton to it. They use vectors a lot in physics to see how forces are applied and different forces are acting on objects. So, but it's the same exact thing as what we just did. Well, we can almost do this faster by just actually subtracting the 2 vectors than it is subtracting the 2 numbers and to do the vectors. So here 4 minus 3 is 1. 2i minus negative I is plus 4. 2i. 3. So again, using a little bit of a cheat because now for subtraction, the way I remember it is head to head, head of the arrow to head of the arrow, because we're going backwards. And our new vector is going to go from tail to tail. So that's kind of what they were talking about in the complex plane. But for this here, it's almost easier just to add and subtract things than it is to try to draw these out. And it works out like these here. Find the distance between the 2 complex numbers. I didn't specifically put this down, but I'm going to go on and write it in because I think it's kind of funny. It's not going to be ha-ha funny, but I just find it interesting. Because they're going to refer to this as, here, well, good if I'm not writing in arrows. We're going to use the formula d is equal to the square root of s minus a squared plus t minus b squared, where the distance between the point AB and ST in the complex plane. And as odd as that looks, it's nothing new. Because we're used to seeing it with x1, y1, x2, y2. But we can't necessarily call it x1, y1 because we don't have an x1, y1, x and y value specifically, or what we're calling an x and y value. But the 2 and 5 here are on the real axis, which is a part of the x. So essentially, if we could think of it that way, the x-axis. The 3 and negative 2 are essentially a part of the y-axis. Okay. And we can plug it in as such. So really, all we're saying is that the distance for this here is equal to the square root of, well, our two x values would be 2 minus 5 squared plus the y values, 3 minus negative 2 squared. I just find that formula funny because it's the same formula we have. We can describe it the exact same way, but because we're talking about the real and imaginary axis, we got to give it different letters for some reason. And out of all the letters, I find it funny that they chose S, T, A, and B. But then we're just calculating this here. And again, at this point, we could have just plugged this all into the calculator, let the calculator figure it out. Negative, negative, make a plus. So here, 2 minus 5 is 3, and 3 squared is 9. Plus 3 plus 2 is 5, and 5 squared is 25. Which would give us the square root of 34. And that's going to be it. Because 2 and 17 are factors, neither one of those are prime, or both of those are prime, and it doesn't reduce. So the distance between these two complex numbers is the square root of 34. So really we're just using the square root, or our distance formula, plugging it in and simplifying. Questions on this here? I don't think y'all need to see another one of using essentially the distance formula. Since we used the distance formula on the last one, most likely we're just going to use the basic midpoint formula for this one here, which just means we add the x values together, divide by 2. Add the y values together, divide by 2, and you get the midpoint. So our x values are going to be 4 plus 2. Our y values are essentially negative 3 and 2. Well, for x, we have 4 plus 2, which is 6, divided by 2, which is 3. Negative 3 plus 2 is negative 1. Over 2 is negative 1/2. Questions on any of this here? We're done.